Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
All right. I hope everyone can hear me. Welcome to this talk today. We have the pleasure of welcoming Girma. Girma is a research scientist at IBM by way of Ethiopia, Italy, Spain, and the UK. He has built a very exciting career in machine learning and its applications to healthcare. And today we are going to discuss and talk about the detection of anomalies and the importance and significance of this problem in the context of healthcare. So the rough structure will be, we have this main part, the exciting part with Girma's presentation, which will last about 45 minutes. And then at the end there, we have a window for questions and discussion together, which we can extend further into this neural network chat that was mentioned in the intro. So this being said, I would hand it over to Girma. The floor is yours, and everybody enjoy.
Thank you, Luis. Let me share my screen and let me know when you see it. Can you see my screen, Luis?
Yes, looks amazing.
All right. Thanks for inviting me. Really much appreciated to be here and share our recent work on trustworthy AI, specifically under detecting and characterizing deviations in data and sometimes model outputs. But again, I would like to thank you, Luis, Matthias, for inviting me, and for Ida for the effort is done to bring me here. So, as Luis mentioned, I am a staff research scientist at IBM Research Africa, where I'm sitting at the moment. As you know, IBM is one of the sponsors for neural network events, has about a dozen global research labs. Two are based in the continent of Africa. One is in Kenya, Nairobi, where I'm sitting at the moment. And specifically, I belong to AI science team, which includes research scientists, machine learning and research engineers. And often we also have interns joining us over the summer. The outline of my talk begins with a bit of motivation on the trustworthiness of AI, which is mostly the reason why we don't see the applications of AI compared to, its theoretical advancement. Specifically, I will jump into fairness of it, specifically understanding deviations in data and what does it mean. I will also share an extension of a similar approach in understanding model outputs and beyond AI datasets. As Luis mentioned, I hope we have a few questions at the end, trying to have a question and answer. So a bit of motivation on trustworthy AI. I think COVID is a very great example, and this snapshot of a paper shows that actually, even if there are multiple papers and approaches reported to perform well for COVID diagnosis and trajectory prediction, it has been really a challenge to get one which is clinically applicable. This is partly due to different reasons. whether it is the type of data, the type of validation, and others could be a problem. But I think we could all pause and ask what makes any AI solution not trustworthy, or why we don't see the application of multiple AI solutions developed and reported here and there applied in a clinical setting. So under that, IBM has been working heavily on trustworthy AI. It's a very bigger umbrella that may constitute different branches. We try to sort them as explainability, for example, that aims to understand how the decision is being made, and what are the determinant factors in your AI pipeline for that particular decision. And that comes along with fairness, especially when you consider healthcare. We all acknowledge the diversity of disease patients across different geographical locations and across different temporal indices. And we aim to provide a solution that's not significantly biased against or toward this particular segment of your data or your population. We also are aware of the challenges of robustness, especially when you consider adversarial attacks. Those solutions should be, safely guarded against such attacks going forward. And as long as data is involved, there is always a transparency issue and the trade-off of maintaining the sensitivity of some of the data, which is even a major concern where healthcare is involved. So in this regard, as I said earlier, IBM research has provided a lot of toolkits, resources to the Linux Foundation, which anyone could go in and play with these tools in order to understand trustworthiness across those different branches I mentioned earlier. Specifically, my focus for today's presentation would be about understanding systematic deviations in data and then model outputs. And this probably aligns well to what we call data-centric AI. Probably in a recent change of paradigm from big data into small and good quality data, we could argue that understanding of the data is actually a crucial step, trying to know what are the limitations, the representation distributions, and so on. And the data could give us better understanding about the follow-up design procedures. That may include selection of architecture, parameterization of them, training and testing strategy, validation, deployment, or could benefit from actually understanding what kind of data we had at hand. Specifically, systematic deviations in data could help you to uncover early in the AI development process if there is a skewed representation across different segments of your population, the quality of mis-annotations, which are often labeled by, for example, domain experts. That could be 1, 2, 3, but they may also have their own, limitations or biases, as you know. This also guides us to advise the future data collection strategy. As you know, when a machine learning model doesn't perform as expected, usually the solution would be like collect more data. But it is crucial to understand what kind of data we need to collect to mitigate those identified challenges. Otherwise, we may even make the problem worse by collecting probably unnecessary data. This could also be extended into model predictions, right? In a sense that you could have a model, you could have a great performance quantified using AUC or accuracy, but usually it is also equally important to understand where the error is happening, how the model is performing across different geographical locations or temporal indices, if there is a conceptual or temporal drift, if there are some adversarial attacks, or how we could detect them actually in the prediction process, and so on. In the future, you may even have new classes that were not seen during training, or samples collected from different environments that could be different hospital devices or weather conditions and so on. So understanding the data and the prediction from model would be helpful to sort of answer a few of the questions that usually come up with trustworthiness of AI. With that regard, I will pick stratification, which is one of the probably old techniques that helps us to understand data. The figures demonstrate shows two examples. The first one is how under 5 mortality in Nigeria is stratified across regions in Nigeria. You could say that in the Northwest region, we may have higher proportion of under 5 mortality compared to, for example, Southwest region. The next figure probably is very common to most of us in a way of understanding COVID disease and its trajectory. It is often easy to see a figure that stratify our variable of interest across, for example, age or gender or ethnicity and so on. This, as you know, is very intuitive to understand how a particular outcome of interest is stratified across a given feature, but it is challenging when you have, for example, multidimensional features in your data. You could do stratification for 1 feature, 2 features, 3 features, but when you have multiple features that may have interaction, which is in the order of higher magnitude, it would be very tricky to sort of understand data from manual stratification. Another one is usually this outcomes are driven by a predetermined set of features. They may sometimes call them protected or sensitive attributes upon which you want to visualize the outcome of your interest. But this, in a way, sometimes limits automated discovery of insights without actually predefining a particular feature of interest. For example, an outcome like for neonatal days in healthcare setting, it may have no impact with a given feature X, a given feature Y, and a given feature Z. But for a certain and anomalous combination of certain values of these features may actually reflect some insight which is not obvious by the domain experts. So we argue automated way of stratifying data that aims to answer those two challenges. One, without requiring predetermined set of features, so that we could maximize the potential of uncovering hidden insights in that data. But at the same time, it is scalable enough for large dimension of data, which is different from manual stratification. I will not go into much of the details, but usually the stratification or our autostrat approach is structured as a sort of optimization framework where we try to identify a subset of data that is different from what we expect. That expectation could be different based on the user, based on the particular problem of interest. But usually we have the null hypothesis where we say everyone is behaving similar to what we expect. But the alternative hypothesis becomes for actually a certain segment of the population, the outcome of that healthcare interest could be more observed or less observed compared to what we expect. And that factor is denoted by Q. And we try to find the ratio between the two hypotheses in order to maximizing our optimization. As I said, I will not go much into detail, but I will just pick one use case we have done recently in collaboration with Gates Foundation and Harvard University. This follows up a research that was conducted in India, a cluster randomized trial that aims to test the validation of a child checklist intervention proposed by WHO. The hypothesis was this intervention could actually be used by care providers so that we could minimize the neonatal and maternity deaths and complications, overall improve the quality of care provided to newborns and mothers. As it's highlighted in this slide, even if this intervention called checklist intervention increase the evidence-based practices by clinical care providers, it doesn't significantly reduce those adverse outcomes on newborns and mothers. Then our question comes, okay, this intervention didn't significantly improve for the treatment arm compared to the control, but is there a subset of the treatment arm that is benefited actually from this intervention? Getting this segment where things actually improved helps to understand, the pros and cons of the intervention, and it also gives us a clue why it didn't work on other segment of the data, and potentially if we need to come up with a new intervention, we have such informing insights to take into consideration. So the first study, before we even try to identify which subsets of mother-baby pairs actually benefited from the intervention, we just ask a very simple question on the data. That is, what are the mother-baby pairs that have highest risk of neonatal death in the data? Probably this is known by the domain experts, but what we automatically identified in the data is actually saying all mothers with first pregnancy experienced neonatal death, according to this better birth data. As you see in the table, there are about 589 mothers in the control arm and 642 mothers in the intervention arm. And the number of living child tells how many children does this mother have other than your pregnancy for which you are getting treatment with. And almost all of them, that's why 100% is shown, actually experienced neonatal death from the data. Right? And this cannot be true, right? And not every mother with first pregnancy is going to have this neonatal days, according to the study. So we took back to the domain experts, people who lead this research in the first place, actually, and they found out this is actually data collection irregularity, which they were not aware in the data. And we found this because we just do simple question without predetermined any feature of interest. And then we identify this irregularity in the data. And once we realize that the number of living child has some data collection irregularity, we discarded it from the analysis and we asked the same question. And in that case, we found actually newborns with low birth weight, which is roughly less than 2.5 kg, are having highest risk of neonatal death, which is almost double with the odd ratio of 2.04 in the control arm and 2.07 in the intervention arm. So the risk is similar in both arms. That's why the treatment doesn't bring significant impact. But you see, we identified something probably obvious to the domain experts. If a newborn is low weight, there is a high risk of having this neonatal death outcome. The two examples I just mentioned tells two things. One, not all the time data-driven insights are new to the domain experts. As you see in this slide, we found something very obvious, but at the same time, such automated data-driven approach actually provides to uncover some insights, irregularities hidden in the data, which the domain experts sometimes may not be aware of, because this is a data with 160,000 patients and then multiple cohorts. So this too gives us, actually, it's always good to sort of bridge between data-driven insights and, of course, with the validation with the domain experts. Then once we understand the data, we jump into the next question where we ask it in the first place. We know that the treatment didn't have significant impact overall the treatment, but what are those subpopulations benefited from this intervention? And for this, we did a bit modified version of our approach, but now the control becomes our baseline upon which we trained a predictive model, and then we test for the treatment, the intervention arm, and the deviation between the outcomes and our prediction, which is now our expectation, shows actually where the deviation happened. And that is quantified with odds ratio of 0.7 for mother-baby pairs, which have normal gestational age and no known number of abortions. This intervention actually helped to reduce neonatal deaths, as the odds ratio of 0.7 signifies. The same approach could be applied to other questions. This goes back to demographical survey data collected in Africa using, again, Gates Foundation. We have two countries, for example, Burkina Faso and Nigeria. And the data shows that under 5 mortality across these two countries actually reduced from about 16% to 12% in Burkina Faso, and from 20% to 13% to Nigeria. These are the kind of reports we often hear. But the question we try to ask is, okay, things are reducing over the years, but are there still subpopulation which are left behind, for which the under 5 mortality is still a concern? Or at the same time, which subset of the population in these two countries actually have even much more reduced outcome of child mortality? So we have the average decline reported in the table. We try to find the two sides of the extremes, the low extreme and the high extreme. And our result shows, for different reasons, the subset of population in the two countries are different for the two extremes. Specifically in Burkina Faso, as you see in the middle line, even if the under 5 mortality goes from 16% to almost 12%, for those people who has Mosi ethnicity and has visited health facility, the reduction is actually much, much higher, which goes down up to 8.9% over the years. For those subpopulation, the data, which doesn't have health facility nearby, as you see in the orange line, the under 5 mortality is still much, much worse, which is 40.3, similar to what has been there about 17 years ago. If you go to Nigeria, it's a different story. In Nigeria, often the region where people live has a determining factor, which may be associated with like other infrastructure in those regions. But our finding shows that actually, even if for average population, under 5 mortality goes from 22% to 13%, you could see for Northwest region, the under 5 mortality is still 19%, but on the opposite extreme, South region has actually demonstrated a very significant reduction in under 5 mortality. The story is the same. We don't have a predefined interest of feature, but at the same time, given an average reduction of value of a particular outcome, we try to identify the two extremes upon which the outcome is over or under observed compared to what we expect. Similar approach could be done just beyond tabular data, as an example to share, to identify new classes or different validations protocol using deep neural networks. This is like a very good example when you have a model trained with 5 classes, for example, but when you try to deploy it and monitor it later, how does it behave if it does see new samples that were not seen in the training phase? These new samples, as I said, could be from new classes or could be samples collected with new validation protocol or laboratory equipment and so on. And we try to validate this work using dermatology as a use case, but the idea is just beyond the tabular data I mentioned earlier, using deep neural networks and their activations, and by setting the expectations on normal data that have been trained on, we could actually easily detect those samples coming through the network with our framework. I also had often an argument when we try to understand data in AI perspective, we tended to focus mostly on what we call AI datasets. Datasets often collected for, to be used as input for AI, and then we try to analyze whether their solution is actually fair, what's the data, and so on. But we have also as a multiple source of data that are not AI datasets. And this include actually academic materials. So I try to argue the story as such even. We tend to use data, which as a ground truth often labeled or annotated by domain experts. And the question is, what if the domain experts are biased when they annotate the data? Their bias could be conscious or unconscious, but it may also come from the skewed representation of examples in their academic materials. If you take an academic expert, they have been trained on in academic institutions for some time, and we need to check if the material they have been trained on is problematic, because we already demonstrated earlier that for AI model, if the data they have been trained on is problematic, of course, the predictions that come from those AI models could also be problematic, right? So the same analogy could be applied on domain experts as well. If the academic materials have been trained on has problematic, if they didn't see enough examples across diversified set of patients, their decision-making where they try to provide clinical care could be also problematic. This problem is actually very common and probably well reported in dermatology domain, where they showed that academic materials used in top medical schools often have a bit of a skewed representation of data from dark skin patients, for example. And this skewed representation of examples in academic materials has actually its own adverse impact in, for example, lack of expert access, delayed in diagnosis. Probably you may not have enough expertise in your area that train on use cases that are familiar to you. Overall, this may increase morbidity and, of course, degraded clinical care at the very end. So a disclaimer, I'm not a domain expert, but we did this work in what we call in collaboration with researchers at Stanford and University of Pennsylvania and so on, which are domain experts themselves, like clinicians. The idea is given different academic materials that could be in PDF, textbooks, and so on. Let's try to automatically digest the content in these textbooks. Specifically, as our first use case, we picked the images in those textbooks, and we apply AI pipeline in order to understand the representation of different skin tones in that particular textbook. Of course, the AI solutions include, first, given the document, we try to parse different entities in that PDF document that may include authors, texts, figures, tables, and so on. Specifically, we picked the image for now. And once we selected the image in a given textbook, we could actually select specifically images related to skins. Once we have found a skin-related image, we could segment the pixels which are actually related to the skin, because some of the pixels could come from clothes, laboratory equipment, and so on. Once we already segmented skin pixels in a given image, we apply pre-trained neural networks to sort of estimate the skin tone. In dermatology, as you may know, the skin tones are characterized as Fitzpatrick skin indices that may include the first ones related to darker, lighter skin tone, and indices like 5 and 6 correspond to darker skins. So in this automated approach, we identified that across 4 well-known textbooks used in the medical schools, most of them have max of 10% of image corresponding to darker skins. And I think this is a very good example of just to look data beyond AI datasets, and 10% could be right or wrong, but at least quantifying that is the first step. And then the next mitigation process could, augmenting the image, providing different examples across different skin tones could be a solution for academic materials, publishers, journals, and so on. But in our overall analysis, we try to understand data, and specifically if there is systematic deviations in data. When we say deviations, of course, it's always compared to your expectation. That expectation could be different. For TAM, that's like the global average in the population. For some, that's predetermined a domain expert setting. For some, it could be like the prediction from another models have been using. But we believe trustworthy AI provides a way to bring the success of AI solutions in academia, research to clinical practices. And this is, as I said earlier, validated with understanding deviations in data and deviations in model outputs, because both the expectation and observed analogy applies for both. But why it is important is often the good question. As I try to demonstrate in my previous examples, understanding data is crucial. And especially in healthcare, where we know that there's a lot of diversity, how a particular disease manifests itself over time, across geographical locations, across different seasons, across different, cohorts of patient, whether it is children, age, gender, and so on. So it is important to understand how things are deviating in our data. It doesn't mean that everything is wrong, but knowing how the quality of your data, first of all, helps you to design the next data augmentation process or new data collection process. This also helps you to sort of, pick the right performance metric or evaluation metric to say this model is correct or not. Once you deploy a model, you could also monitor it over time. Probably this is something most of you are aware. There is, temporal drift. There is also a concept drift that changes over time. As we demonstrated in our example earlier with the better bus, interventions are applied here and there. We often get a report that whether this intervention actually benefited or not, but we should always remember that interventions could benefit a subset of your population very different from the other. And identifying that subset, characterizing it, could give more insights for, of course, domain experts, policymakers, and machine learning researchers to come up with, better and improved solution going forward. As a disclaimer, I mentioned I'm not a domain expert, but most of these works we have done have been actually in a great collaboration with, public health professionals and funders and researchers and domain experts themselves to validate. I argue that the aim of data-driven method should just to provide insights, even if it follows its own statistical significance and characterization with different metrics. It is very, very important to have a say by the domain experts, as we demonstrated in that better bird study, where we first identify irregularity in the data, we communicate with them. Once it is corrected, we found an insight which is obvious to the domain experts. So I think it is often my great argument and recommendation in AI pipeline, especially in AI healthcare, to involve those domain experts at each and every design steps of the AI pipeline. I think by this, I tended to wrap up my presentation for today. Again, thanks for sharing your time and hear about our experiences here at IBM Research Africa. But most of them, as I said earlier, have been done in a great collaborative framework with other global labs at IBM and, of course, institutions outside IBM, including different universities here and there. Please, ask questions. I would love to discuss with you. Here is my contact detail in case you want to follow up with more questions, feedback, and comments. I think let me stop here. Luis, let's hear if there are questions.
Yo, thanks so much, Goma. Amazing, very interesting. So let me have in parallel this Q&A open. Okay. And Julian, if anything comes through, I have my eye on it, and then we'll integrate it. Let's start with thanking Goma again. Very interesting work and great presentation. And as you guys all have seen, I mean, Girma is kind of at the bleeding edge of this all over the world, but also in particular in Africa, organizing lots of workshops. So if you are around, make sure to check where you can find them, because it's usually a great pleasure to be in one of those workshops and interact with them. So that just to kind of round up the collaboration part. But yeah, let's dive into the topic. So for me, like my first question, like if we come from ML, right? One of the first things you learn in machine learning class is how you can decompose the generalization error into bias, variance, and then some irreducible component. And I'm wondering, after like or being involved in this work and thinking about this so much, what is your recommendation in terms of this trade-off when kind of telling people how they should go about using or deploying machine learning in any of these settings that you mentioned? Could you comment a bit on that?
So if I understand correctly, how do I see the analysis of errors in machine learning models, and how machine learning researchers, practitioners should sort of, deal with them? Is that the right understanding of your question before I start?
Maybe, yeah, to put it a bit more specific. So what I specifically meant with the bias variance trade-off is that usually you have to make this trade-off between either biasing your estimator, so making some like going away from the kind of the true relationship that you are trying to model, or you increase the variance and you have the risk of modeling noise. And it seems to me that this is a question that also pops up in these topics that you discuss, right? So let's say we have an ML model and it's a very good pattern recognition, like just a brute force correlation machine when you train it in a supervised way. And if you want to deploy it or want to use that technology, right, you always have to somehow make this trade-off of saying, okay, I either it's going to work on this data, but it might perform worse on a subpopulation because I have bias, or I either artificially include some augmentation, things like that, or some bias penalty, and I make it kind of focus less on the specifics of this data at the benefit of having less bias, but then maybe you increase also the error. So I'm wondering kind of how what is your position towards this trade-off? So would you recommend people to say develop 3 models for each subgroup? Would you say rather have one model which is maybe a bit worse in performance but has less bias overall? Like, this is where I'm trying to get at.
Yeah, I mean, that's very broad in a sense, and I will be very careful to comment what is the right way to do. But I have this perspective in it. We should be really careful in quantifying what is the best optimal point between bias and variance, or between generalizability and personalization, in a sense. Of course, I think we probably could agree the right way forward is like all these solutions governed by the right rules and regulations by, governmental, continental, and so on. That's probably the way forward, to have certain guideline, what sort of criteria we should evaluate a model on, and what should other things to be avoided. That is probably for sure. But beneath that greater guideline we need to have as quickly as possible, as myself as a researcher, what I tend to focus is like domain experts probably are well aware of to say what's right and wrong, rather than machine learning researchers, for sure. In a sense, that you could sometimes have some bandwidth to accept a certain level of bias or variance, and how that's quantified with resource, time, money, and so on is another follow-up sort of quantifications. But the right way to go for me is trying to understand what's happening at the moment. And if you are biased, which subpopulations are you biasing? How much, what's like the severity level of that biasing versus the other way around? And this should be open for discussion. Of course, when you have that decision, you include different criteria in picking which one is right? You may sometimes benefit less resource intensive and probably generalize better if you are, for example, working on a disease which is like contaminates and thousands or even more people could be have that impact, and you want an assistive method that sort of filter out the diagnosis process. There you may have better sort of bandwidth to accept some irregularities, but you go to other disease types where one mistake could be catastrophic. So this is just to say that I don't think there's one solution. Specific varies from domain to domain, problem to problem. But as a researcher, I always think that the domain expert should have a major say on deciding what's like the optimal point between the two. And as I said at the very beginning, all this could be well governed by well-studied regulations and guidelines everyone needs to follow, maybe going forward.
All right, I have a follow-up, kind of a devil's advocate question for this domain expert, but first let's go to the chat. So Christian asked, how does automatic stratification differ to classical clustering, and how should we come up / deal with the pervasive labeling when training a model? So how does automatic stratification differ to classical clustering, and then how to deal with the labeling when training a model? I think that's two kind of questions in one, basically. Any comment, Gemma?
Great question, Christian. The first one is how automatic stratification differ from classical clustering and even other stratification techniques which are being reported recently. Probably similar. They try to identify segment populations, but our focus, at least at first, is like trying to have one outcome. When you cluster, you may cluster them accordingly. In a sense, sometimes you may not have even a very clear and description of cluster A versus cluster B, and in a way interpretable by the domain experts with few and selected features. Second is when you try to compare our automatic stratification with other stratification techniques, that's include pi subgroup, slice finder, div explorer, which are very recent actually on tabular data, we tend to have two advantages. One is when we quantify a subset, we try to see the size and the severity of the divergence. You have a few methods that just pick one or two samples in your 1,000 or more population that say these two individuals are very extreme, but we try to say that extremity is also normalized by how big the size is. So that's what we consistently find ourselves different from those mentioned stratification techniques. Second, most stratification techniques come up with like getting one value per feature. For example, if you say gender, it just picks female. If you come to age, it just comes less than 50 years or greater than 50 years. But we have that into an extended space where we also have logical ORs. That helps us to identify different segments of the population, but they could be different for the same reason. And just for the Christian, that's like how we try to try to deviate ourselves from traditional clustering or very recent stratification techniques. When you come up with deal pervasive labeling, I think our is like more stratification in a sense. you try to identify first this pervasive labeling itself by setting your own specification and context on why a certain label should be different. With that, you also have missingness and so on. So the good advantage of automatic stratifications is actually the flexibility to change your outcome of interest, one from labeling from another variable and others to sort of divert that one. But all the time, I don't think we could completely avoid that problem, but at least you could have identifications and characterization of where those labeling happened. That's my say for Christian. Do we have a follow-up question from Alex?
Yeah, I think that's on its own presentation, basically, right? He's asking what your thoughts are on responsible AI. I don't know if responsible and trustworthy could be synonyms. If yes, then you got the answer just now. But any more comments?
I mean, I probably as a bigger umbrella, we could say they are similar, at least its aims to both of them try to develop AI solutions, which could be, clinically or, it could be deployed in real life. I know responsible AI is also a line of work. I myself participate in a responsible AI framework happening in Canada, where we try to shape what are the rules and the type of biases one needs to consider when you collect the data, design the model, develop and monitor. But I found it myself, responsible is a bit more subjective than trustworthy in a sense. When you say trustworthy, you have a solution. Who is going to use it? Do they trust that solution? When you say responsible, that becomes a bit more blurred, but probably I'm completely mistaken. But I think the bigger umbrella for both is like trying to develop a solution that makes positive social impact, which is a theme of for good seminar.
Yeah, Alex, does that cover your question? If not, please let us know in the chat. I have maybe one just follow up to the second part of Christian's question with respect to the labeling. I mean, you hinted at this with, this editorial paper also that you wrote on, creating data or creating data sets for trustworthy AI or all these types of experiments that fall under the umbrella of trustworthy AI, because it is true, right? Usually the bottleneck or the Achilles heel for any types of any of these analyses is that you need the metadata to form the subgroups, right? Like if you don't know the attribute, you cannot check whether there is a bias. Yeah, I do agree, like that this is actually one of the, it's maybe not a complicated problem, but it's a big problem that a lot of the data sets don't have this rich metadata that enables the types of analysis that are necessary. Or what do you think? Is it different?
That's very true in a sense. And the reason why we stress the use of metadata actually, that checks a box for me, because we need to understand the data. Don't just give me a million image data set unless I could have some metadata description to stratify to understand the data better. And this underlines when I said search stratification even helps us to inform our next data collection procedure in a sense. Yes, we need to do that, but if we don't have the data, of course, we try to still generate a few attributes from the data in order to make us understand better. But when you said most AI data sets sort of don't have that metadata, it actually reminded me my sort of strong argument often trying to understand a particular problem just from one modality. Take a particular cancer, you just take some X-rays, some image modality, and you try to understand everything about that disease from one modality, which is not actually the way human beings understand a particular problem. The right way is to give multiple modalities, multiple streams of channel upon which we could learn a particular problem. So I have a big question mark often trying to understand bigger problem just from one modality, right? beyond that, of course, we need to have that metadata, even if it is image, where it is collected, at which season, at which time, which patient, which device, what are the environmental conditions associated with that data collection. We need to get all those details as much as possible, because those are the details we want to sort of understand the data, explain the decision-making process later and in a better way, right? If we don't have, of course, we try to, sort of get a proxy for those attributes, even trying to infer some features given image modality. And a very different topic of my research, we work on generative models and material discovery domain. So given a molecule, we try to, predict the features, the toxicity, solubility, how drug-like it is, just given the molecule, and we use that analysis later. So I think we could follow the same approach. If you have just image data, try to predict still some attributes and trying to understand the data and the prediction better. So we need to have multimodality first. Even if it is one modality, we need to have multiple metadata to understand it. Even if we don't have that, we need to sort of have a way to create them to understand them better.
All right. So then, if we have a few minutes left, then let's maybe revisit and bully a bit the domain experts. And I mean this as a joke, obviously. So I mean. Just to be transparent, obviously I agree, like you need domain experts, and that's usually where it gets interesting in terms of the also kind of this iterative discovery when you do experiments like you do, to kind of check back with them. But I was really fascinated by this last or one of the last works you showed, where you flip the script a bit on this typical bias narrative, right? Like usually the papers you read in the space is something like, okay, this model and it's on this data, and look, it's doing all of these things, and this is why it's bad. And the way I understood what you guys did there is you basically use machine learning to look at textbooks, right, and try to understand what are the people, the domain experts who are being schooled by these books, what are they seeing to do their job, and what kind of bias is encoded in that data. And that I find this it's a very curious and cool flip of the script in itself. But maybe more broadly, I mean, if the overarching goal is not just to understand bias in machine learning, but maybe also to bring about change in terms of patient benefit, things like that, like healthcare delivery, where it's really about making sure that we have some level of fairness in delivering certain services. Is it really the case that the domain experts are the gold standard? I mean, to me, it seems to suggest actually your analysis maybe not, or did I understand the conclusion wrong?
I don't think you understand the conclusion wrong. I still, that's like my strong argument. It doesn't mean that domain experts are always right, but what you could do is always trying to navigate this area together. And the more communication is there, it's better, because as machine learning researcher, you have not a lot of domain knowledge you could even input and inject into that model, first of all. And second, what you get as from machine learning perspective should be interpreted its significance by the domain experts, because usually I tend to understand AI solutions are ways to assist domain experts, human, to do their job better and in an efficient way. So for that regard, I have good argument about involving them at every decision process. Usually the problem or the challenge I see is like, this is a model, very complicated, and this is how it performs on this given data set. So sort of use it. that probably discourage that, synergy between domain experts and researchers. Rather, we should involve them from the data, understanding the data, and what should be the model, whether it's logistic regression or transformer, and what does this analysis accuracy mean, and what's clinical significance, and what are those errors, why we are penalizing this subpopulation compared to this. Is this because the disease changes pattern over the years, or the training that has a different spectrum? So that communication is always needs to be there, but at the same time, we should, from the example you just picked, we should be aware also domain experts could have their own conscious, unconscious bias, right? And with that, I don't think they have the absolute right and so on, trying to validate things. Such methods could help to actually uncover some of the bias they may not be even aware, as we demonstrated with the academic materials. And if they are doing annotation, we could still use data-driven stratifications to ask them what are the strong and weak points when they do annotation. Probably it's not aware for them, but we could say, we just found out you annotate these samples very differently compared to this. And that opens a bit more discussions and insightful discovery for better of the two sides.
All right, so we have a kind of a peace offering to the domain experts. Nobody is being bullied here. That's nice, and it's also a good point to transition over to the neural network. So I understand that there is this networking environment where if you have questions to Germa, you can put them. He can check this, I think, also at a later stage and come back to you. Otherwise, you had all the socials of Germa available on the slide. Maybe Julian also can reshare that in the chat. So make sure to follow Germa on Twitter, LinkedIn, and check out his great work. And yeah, with that, I would say let's close the presentation part of this event. Germa, do you have any last words?
No, not really. Thanks everyone for your time. Don't hesitate to contact me as via Luis, or I leave my email contact there. But again, thanks for Matthias, Luis, Ida for having me here.
Germa, thank you so much. It was amazing. Looking forward to all the future great work you will do. And also Julian, thanks for organizing, and all you guys for attending. So see you around, and bye-bye.
Participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
Mm.